recording too. Good afternoon, everybody. We're going to get started with the next talk. I'd like to introduce Kevin, who's going to be talking about building high throughput systems with Python.
Hi, so yeah, again, my name is Kevin. I work for a company called Ballard. We build a data platform for retailers, and we deal with some fairly high traffic rates, low latencies, and we use Python to do pretty much all of it. So today I'm going to talk about a project called Taba, which is a distributed event aggregation service. Basically what it does is it helps you instrument your code by putting calls to record events, and then those get aggregated into a central location where you can then query them. So for example, we can record the particular win price of a type of bid and then query it for example, the 10-minute sliding window and some percentiles. So Taba is built using Python. It uses Redis as a backend store. We have a cluster of those instances. It makes heavy use of gevent and does some optimizations using Cython. And it does a fairly high ingest rate, uses multiple, over 100 different processors, so it's a relatively large-scale deployment. So instead of talking today about the architecture and how it's implemented, I thought it would be more useful to talk about some of the lessons learned when trying to build large-scale distributed systems using Python. So lesson number one is get your data model right. So any given problem has a number of different ways you can solve it, a number of different ways that you can model it. And the one you go with really limits or informs what your application is capable of doing. And some very subtle differences in the way that you model a program can have massive impacts on your ability to perform later. And once you've committed to a model, it is extremely important, or it's extremely difficult to go back and change it, especially in a distributed system where you have things deployed all over the place and you have protocols between different components. It's very hard to change. So at a high level, this is kind of what the data model for Taba looks like. You have a large stream of events which are generated by clients. Those get aggregated into these state objects, one per tag, which is essentially the metric and the source. And those get stored in a database. And then when you perform a query, the states that match that query get combined into an aggregate. Those different objects look like this. So an event is basically a tuple of the name, the type, the time, and some payload. And in this example of a moving interval counter, the state is basically some bucketized counts and totals over a certain time range. And those states are stored as compact, efficient binary objects, so that because they go over the wire a lot, they get edited very often, so they're extremely efficient in terms of space and mutability. The aggregates are responses to queries, so they're the friendly JSON text that you'd want to consume by another service. So one way we can respond to queries and go between states and aggregates is to convert each state into an aggregate to the simpler representation and then combine those together. So require that every counter type or every metric type has a way to combine those aggregates. And this seems like a reasonable thing to do. These aggregate objects are much simpler they're much simpler schema, so they'd be easier to implement a way to combine them. However, there's a problem with this approach, and if you're sharp, you may have picked up on it. You can't cache this, right? If you were to cache the projection and aggregation ahead of time, you would be losing some of the data. Like you lose the temporal data in that efficient state representation, and so you can't actually respond to queries correctly if you cache that ahead of time. So the solution is to change the model so that you provide a way, or you require that there's a way to combine these states together. And by doing that, you can actually cache those combinations ahead of time, and you can respond to queries almost instantly. And changing the model in this way has another benefit in that you can actually do pipelining. So instead of having the requirement that all of the incoming events have to be combined directly into the database when it's available, you can actually convert them into partial states and then combine the states together because you already have that primitive. So these examples are very specific to Taba, but the main takeaway is that the model, the way that you treat data, the way that you flow data through a system could mean big differences in performance, even if it's small differences in the way you handle it. So the small difference between projecting and then combining versus combining and then projecting means that queries can be responded to in a matter of milliseconds as opposed to a matter of minutes. So lesson number 2, state is hard. Maintaining consistent and durable state is a very difficult problem. It's one of the most fundamental problems of computer science. And there are a lot of tools out there that do this very well. And whenever possible, you want to not reinvent that wheel. You want to offload the state into subsystems that are designed to handle it, which are basically database systems, or offload it to your clients. This is the basic architecture of the Taba backend. So in the center there, we have the cluster of Redis instances that store all of the state in the system. It's a hardened subservice. It uses master-slave replication, uses sentinels for failover, does periodic snapshotting on offsite backups. That small component of the entire system is very well protected, and it uses a lot of the features of Redis to maintain that consistent state. The rest of the system, which composes of these front ends and back ends, which run a number of instances of the Taba server process, are completely stateless. And actually, the front ends and back ends run the exact same code. It's the exact same image. The only difference is the traffic that they get sent. And because those are totally stateless, the actual state they have is whatever's in their working memory, whatever request they're working on now. And those requests are always stored somewhere else while they're being processed. Because of that, this is very resistant to failure. So if any of the front ends go down, any of the back ends go down, it doesn't matter. Their traffic will just get simply rerouted somewhere else. It also means we can very easily scale up and down based on the current load. So if we need to handle a spike, we can double the number of servers, it doesn't matter. Or if in the middle of the night, when there's not a lot of traffic, we can shut down half the cluster. And we actually do code pushes in this way. So we have a little script that when a machine boots up, it downloads the latest code and starts running it. To do a push, just upload the latest bundle, shut down the entire cluster, start it back up, and it starts up with the new code. So lesson number 3, this is an interesting pattern that comes about when using greenlets and generators. They work extremely well together, especially in processing pipelines of data. So this pattern that occurs a lot in the Taba code is the concept of an asynchronous iterator. So basically what it is you have this object which acts like an iterator. Technically it's a generator. It has an input queue of objects that it's processing from a source iterator, and then it has a number of greenlets that are acting as workers, and an output queue that is exposed as the output of the iterator. And the trick is that the in and out queues are of a fixed size, so that when you try to put something into a full queue or remove from an empty one, that current greenlet will block. And then when greenlets block, what they do is they switch to another one immediately. So you can actually chain these into a long series of processors that will basically jump around to wherever in the chain currently requires processing. And you can, because of the way gevent works, you can actually hide some fairly complicated network work inside these worker greenlets, and when you hit the network, it'll jump somewhere else. So you can do real-time processing on a stream of data without having to explicitly either do full batches or do synchronization between different points in the chain. It kind of happens automatically. So the last thing I want to talk about is, so this is specific to CPython, and I'm assuming a Linux system. It does suffer from memory fragmentation. And actually, there are a couple of really great talks earlier today about memory management in Python. And I won't be able to go into nearly as much detail, but I think it bears repeating here. So fragmentation is when a process heap is inefficiently used. That is, the operating system will report a much larger number in terms of the amount of memory used than the garbage collector will, and they'll both be right. And the reason for this is that you end up with lots of chunks of memory which are not optimally usable. So fragmentation happens by, so say you start with a heap that looks like this. It's perfectly allocated. Your application continues to execute, and as part of the execution, you'll free up some blocks of memory. Some blocks will be allocated, and at some point, you'll want to allocate an object of this yellow size here. And that object is smaller than the total amount of free memory, but because objects have to be contiguous in memory, there's no one place to put it. So you have to, what ends up happening is that the interpreter will have to go back to the operating system, request more heap, and then put it at the end. So the ways to fight fragmentation, you want to avoid large numbers of small objects, because small objects tend to get placed wherever there's space for them in the heap, and that's mostly true. There's some optimizations that the interpreter will actually do for very common objects like tuples and lists. But generally, small objects will get placed arbitrarily throughout the heap, and then when your request that generated them completes, they'll get collected from arbitrary places in the heap. You end up with lots of little spaces. And this gets much worse if you're dealing with a combination of a few large objects and many small objects, because then there's never a good place to put those few large objects, so you end up always having to keep growing the heap. So another way to fight fragmentation is to minimize in-flight data. So less memory used means less memory fragmented. And generators, like I mentioned earlier, are a really great use for this. And also a good piece of advice in general is, whenever possible, reference, don't copy. So we use another technique in Taba where we'll actually use Cython, which, for those not familiar, Cython is a kind of a hybrid C-Python language where you can switch between the two, basically line to line. So we use Cython to go down to the C level and do manual memory allocation on a particular type of object. And we then hand those objects off to the GC and let it handle it normally. So say you have this request coming in. This is an HTTP request with some JSON data. What you would normally do is decode that, and it would generate lots of little strings and little reference objects, and they'd go wherever it can find them and some place for them in the heap. What we do instead is that we decode it in Cython, and then we allocate page-size blocks of memory that point back to ranges of text in that original blob of data. And at first pass, that seems a little inefficient because you could be allocating an entire 4K page just to hold a couple of pointers. But the main takeaway is that by putting pieces of memory that are related next to each other, when you end up finishing that request and freeing the memory, you get large contiguous blocks of memory that are freed all at once. And large blocks are more useful for storing more incoming data, and there's also a much higher chance that they'll get released back to the operating system. One more thing I want to talk about is the concept of ratcheting. And that's kind of a pathological case of fragmentation caused by the fact that the heap has to be contiguous. And they're a little asterisk beside contiguous because that's not 100% true. It depends on the platform and the allocator you're using, and some allocators are worse than others. But for Python on Linux, using the standard allocator, this is mostly true. So say you have this heap, it's fairly efficiently allocated, and you get a request that requires you to allocate a really big chunk of memory. So you have some really big piece of text you need to store. So it goes to the operating system, requests a whole bunch of heap, and it puts it in there, and everything's fine. So you continue processing your request, and at some point, some background process runs and allocates some small object and decides to place it right at the end of the heap. Now your request completes, it collects that big blob of data, but that little object that was allocated in the background sticks around. And because there's that one little object right at the end of the heap, it can't shrink. So you end up in a situation where you have this really terrible memory usage, and you can't free it to the operating system because of one tiny object. And this is just a basic limitation of the way CPython is implemented, it can't move objects around in memory once they're allocated. So yeah, basically there's no way to move it, so you can't shrink the heap. So some ways to fight this. Avoid persistent objects. Sockets are really common offenders here. Especially in connection pools. So when your application's under its highest load, that's typically when it's using the most memory and when there's the most pressure on the connection pool. If the pool is implemented poorly, it'll actually allocate a new socket at that point. It could stick it near the end of the heap, and if it does that, that object will never die and you'll never be able to shrink your heap down. So you want to avoid persistent objects as much as possible. Everything should have a lifetime. Caches are another good example here. Everything in a cache should have a finite lifetime. You should always try to clear out anything cached. Anything that has to be persistent should be created when the application starts up. So as soon as possible before you start processing any data. And by doing that, you'll get pretty much all of your objects fairly compactly down near the bottom of the heap. And so you don't get this issue where you have long-lived objects near the top. And obviously, avoid letting the heap grow in the first place. Again, less memory means less fragmented memory, means less ratcheted memory. So yeah, that's all the lessons I had for today. The code for Taba is up on GitHub if anybody's interested, and I'd be happy to answer any questions. Oh, yeah, for any questions, there's the mic in the middle here. Anyone?
So I wasn't able to make it to the earlier talks on garbage collection, but you were talking about this fragmentation problem in the CPython. Is the same true of PyPy? Are you aware of that?
It's a good question. It's not. Fragmentation is always an issue in dynamic languages, but PyPy is able to move things around in memory, so it can do periodic compactions, and you don't get nearly as bad performance, or you don't get nearly as bad fragmentation or ratcheting. Yeah.
Hi, thanks for the talk. We've done a little bit of benchmarking with a gevent in terms of concurrency, and in a very artificial kind of sense, like most benchmarks. We ran into like a CPU, like it just used so much CPU. That was the first thing it ran into. You seem like you're doing lots of concurrent requests with gevent. What was I guess the first thing that you ran into that stopped you going more concurrently, and how did you get around it?
So our bottleneck was actually network I/O, and for those kind of use cases, gevent is great because it's designed specifically for switching context on I/O. Personally, I found that gevent is pretty good for any workload that's not CPU bound. If you are CPU bound, though, it's actually it has a lot of problems because it uses a non-preemptive model. So you can actually end up in a state where one greenlet will hog the CPU for a long time, and that actually prevents anything else from happening, including responding to other requests. So gevent is great for network bound, not great for CPU bound loads.
Thanks.
Yeah. Well, if there are no other questions, I want to just thank you for listening to my talk.